Okay, hi guys, and welcome back to number 2, workshop 2 in our attack detection fundamentals series for 2021. As promised today, we're looking at some macOS detection. I'm thrilled to say that we're joined by Calum and by Luke. So both of those guys are kind of offensive security consultants within our F-Secure consulting business. They've done some really great stuff, so I'm looking forward to you guys seeing what they've done. Just to give you I guess a brief recap of the series as a whole, for those that have joined before, I'm sure much of this is very familiar, but effectively goals of this series, ultimately we're trying to improve understanding of offensive tradecraft, so we can help to detect and maybe even prevent some of that from happening. Much of the stuff that we're going to show you is as the series title suggests, fundamentals, so things that we think are likely to be under the hood of the enterprise products that you already rely on. So it should give you some idea of just how those things work, how they come together, and maybe even some of the limitations on what that could provide you. In terms of how we're doing that, just as before this series and the last, so we're going to analyze some TTPs used by real world threat actors. We're going to emulate those in a controlled lab environment and observe, as the title says there, observe the traces that they leave. I think the important thing, as hopefully has come across, is that we're trying to make the content that we deliver and the labs as repeatable and easy for you to digest as possible. So a recording of this workshop can be found on YouTube probably tomorrow. Slides for everything you're seeing are also going to be available tomorrow, and indeed the lab guides for the labs that the guys are going to cover. All of that, it will be available. Well, it's available right now, and obviously you can digest that in your own time, go back through the recording, whatever you need to do to hopefully maximize the quality that you get out of this, really. So in terms of the series overview, again, hopefully familiar to you. So we switched up for 2021. So rather than doing an end-to-end Windows-based kill chain, we're going to look at a variety of different technologies that hopefully for everyone will have some relevance. Which means that for each of the workshops, there'll be some aspect of an end-to-end kill chain, maybe not all of the steps, of course, but the attacks that you'll see cover various steps from the initial access through to discovery, lateral movement potentially, and so on. So today, as promised, we're joined by Calum and Luke, and they're going to be delivering our macOS detection workshop. So I'm going to hand over to those guys to take it from here. So cheers, guys. Thank you.
Okay. Awesome. Okay, so cheers, Alfie, and welcome to workshop number 2, macOS edition. So yeah, we're going to be covering kind of an introduction to detection on macOS. We're going to look at a few different TTPs. We're going to look at a lot of the native macOS defensive controls and kind of talk about how they work, how they can be bypassed, how they can be utilized to defend against things, and kind of how that all works. And crucially also, for those of you that are kind of new to macOS detection or have kind of roots in the Windows side, we're going to talk about some of the key differences between Windows and macOS. Okay, so to start, some telemetry sources. Some of these are very familiar to those of you with Windows experience. Sometimes there's quirks. Apple kind of have their own restrictions on how a lot of this stuff works, and as kind of security vendors and security professionals, we kind of need to fit inside that to get some stuff done. So kind of going through networking is very familiar. Firewall and web proxy is obviously the same. There is something called a network extension, which is something you can do on the endpoint, and we'll talk about that towards the end of this workshop. We've got endpoint logs. There's something called the unified log, which is Apple's attempt to stick all the logs in one place. So if you use console.app on a Mac device, you can see all these logs and query them there. There's other things like SSH logs and a tool called OSQUERY, which again, I won't spoil too much, we'll talk about it shortly, but is a way of getting information from your endpoints. Not macOS specific, but useful in this case. And then whilst technically an endpoint log, it's very kind of different to the Windows world, there's something called the Endpoint Security Framework. And this is a method for security products to find out about process executions, file operations, all kinds of things that you might want to detect and also prevent. So super quick agenda. We're going to start with talking about our C2 framework of choice, which is MYTHIC. We're going to talk about Office macros, and then on the defensive side, how sandboxing and ESF works with that. We're going to talk about launch agents and daemons, and then again on the defensive side, we're going to be talking about code signing and OSQuery. And then lastly, we're going to talk about bypassing a control called TCC, and how network extensions play into that as well. And as Alfie mentioned, we have 3 labs for you to go to. It's not intended for you to go through these now. You can do these in your own time. They'll be up on our labs blog. Well, they're up there now. And you can work through these. We'll kind of cover some of the basic topics and kind of walk through with a video with some of the key themes. Cool. Okay, so starting with a really brief introduction into MYTHIC, something that was previously called APFELL. Okay, so MYTHIC, it's a C2 framework. It's very extensible, very pluggable. It was kind of written with customizability in mind. It supports all platforms. It's not something specific to macOS. There's agents for pretty much everything now. We're looking at it because their Mac agent is really cool, and historically, when this was first released, it was called APFELL, which is now what the Mac agent is called. It's developed by Cody Thomas at SpectreOps, and is outside of macOS. Is just really, really cool. So go take a look at this. As I said, we're not going to go into like super depth about how this all works. We'll leave that for you to explore in your own time through the labs, and the documentation is really, really good. I do want to focus slightly though on APFELL and JXA, which is the agent we're going to be using throughout this workshop. A lot of our examples use it. So what is JXA? JXA stands for JavaScript for Automation, and it's a programming language that is on every macOS device. You can think of it kind of like PowerShell, in the fact that you can access native functionality of the OS via a bridge. So the JXA Objective-C bridge lets you call native Objective-C functions, which makes it really, really powerful when doing things like payload development. If you just take a payload, it comes as a JavaScript file. You can execute this with OSA script, a command line tool on a macOS device. There's other more OPSEC-friendly ways of doing this. You can embed this code in actual Objective-C files, and a few other things, but we're going to be talking about the more basic side of it for now. I will say it's a bit of a pain to use and debug. JXA, that is, not APFELL. APFELL is really cool, but thankfully a lot of the hard work has been done for us. Okay, so then jumping into our proper first topic, Office macros.
Cool. Yeah. So to kick things off with the kind of offensive side of things, it's probably worth noting that we will be doing a lot of kind of offensive work, despite the fact this is a detection workshop. The kind of underlying premise here is show you how the offensive side works. It makes it a lot easier to understand what you're looking for on the detection side. So to kick things off, Office macros, yes, we are talking about macOS, and yet we've somehow managed to drag Windows into this. But it's not really something worth overlooking, and it's quite an interesting area on macOS. So for those of you that have worked in the offensive security space before, you'll be more than familiar with macros. And for those of you that haven't, they were the #1 most common infection vector in 2018. They have been a huge problem for Microsoft and Office products for years. And until kind of recently, Microsoft have started bringing in some kind of attempts to prevent this and some virtualization stuff, but we're not going to get too into that. So look, if you wouldn't mind just kind of moving that onwards. So to kind of give a few examples, we have seen this used in the past. We've seen Lazarus Group back in 2019. We're using it as a way of kind of getting a backdoor on target devices. We've seen US fraudulent government documents that have got macros embedded into it. And again, it's just the same kind of thing. We've seen this in Windows for years. It's going to translate over. Attackers don't have too many fresh ideas on that front. So to kind of break down Office macros for anyone that isn't familiar, they are developed in Visual Basic. Same thing on macOS as on Windows. There is some kind of auto-open functionality. So when a user opens a document, provided that they kind of click through all the prompts and security warnings and all that kind of fun stuff that users love to click on, we will begin kind of executing whatever payload we actually set within the document. So macros are kind of really powerful, and the reason they're of interest, especially to attackers, is they have some kind of ridiculously overpowered capabilities. So you can execute shell commands on or through macros, both on Windows as well as on macOS, as we'll go on to look at in a second. Interesting, we'll kind of touch on this in the next slide, but it's worth noting that when you spawn a macro and it creates a child process, that child process inherits the sandboxing of the parent process that created it in the first place. So for those of you that are unfamiliar with the term sandboxing, sandboxing on macOS is effectively a way that Apple try and kind of restrict what an application is able to do. So what resources it can access, what components of the device it can access, just kind of different functionality that an application would need, or more importantly, what it doesn't need. So the kind of general idea here being, how can we restrict an application to have only what it requires for legitimate usage? So if it's compromised, it's not kind of game over. So like I said, we're going to do some offensive stuff here. To give people a bit of an idea, this is the Office macro that we're going to be using today. It is pretty simple. This was generated using a tool developed by Cedric Owens, who effectively just created a tool that will go away, download a APFELL payload, as you can see there, add executable permissions to that payload, and then execute it using OSA script, which Luke mentioned earlier. Cool. So at this point, if we manage to get this kind of macro running on a device, we land on what we think looks like a shell. It resembles a shell. We can kind of ls, see what's in the current directory, and it seems like we've kind of got exactly where we need to. And then we start trying to do things like reading from the user's downloads folder, trying to write to certain areas of disk, and we start running into this kind of operation not permitted stuff. Now, this is all part of Apple's whole sandboxing side of things we've mentioned. So it can be a little bit frustrating. You're then stuck there. You've got almost like a half shell type thing. So at that point, it kind of seems like it's game over. At least that's what you would hope. Look, if you wouldn't mind jumping on. Now, to kind of look into where this whole sandboxing comes from, and to kind of reflect on where we are just now and how certain functionality is possible, we can see within the entitlements for Microsoft Word that it has the sandboxing entitlement. We can also see that it also has the network client entitlement, which is how we're able to get the likes of a C2 callback from a document, even if it is, or even if our APFELL payload is running within a sandbox. Obviously, that's then permitted to use the network client, makes your life a little bit easier. So, like I mentioned, you would assume and hope that at this point that the sandbox has worked, that we have kind of covered it off, and that we're going to be extremely restricted moving forward. But as I'm sure we all know, working security, it's not quite as simple as that. And that is thankfully because there seems to just always be a sandbox breakout out there somewhere. We've seen the sandbox within Office documents been broken numerous times by numerous different people, whom I won't go into mention just now. But the general idea is the sandbox is a great thing to have there. It's a nice little initial hurdle. But we're going to show today how it doesn't necessarily stop people kind of achieving what they would go on to achieve on the device. So to understand the sandbox breakout that we're going to look into today, we're probably best looking at where it kind of originates from. So if we go and look at the actual entitlements and more importantly, the exceptions of those kind of entitlements in the sandboxing, if you like, one thing that's pretty interesting and stands out to us is this regex we have in here, or regex, whatever you fancy calling it. Now, I'm sure there's be a lot of people watching this that are better with regex than I am, will understand this far more than I do. But the general understanding of this regex is it permits users to be able to create, permits the sandbox process to be able to create a file that begins with a tilde and a $sign. Now, this is presumably based off of Apple's Microsoft Word's legitimate functionality, where it writes temporary files to disk. So for those of us that have messed up on countless occasions and accidentally closed their documents, and we're able to go back and recover from kind of recently saved documents, or kind of that recover functionality that Word has, it's a lifesaver. But in this instance, it's also provided us as a way, provided us with a way of being able to write files to disk, kind of bypassing that sandbox restriction, if you like. So the attack we're going to perform with this, how we're going to abuse that exception we've just discussed within the sandbox, is we're going to create a zip file, so a zip archive that begins with tilde $, and then whatever we want to call a zip archive. We're going to drop this into the user's home directory, and within that zip archive, we're going to have a ZSH environment variable. Now, ZSH environment variable purely because the kind of recent versions of macOS run ZSH, but this will also work depending on your environment with likes of bash profiles and other kind of environment profiles that are going to be loaded upon the likes of a terminal instance been started or being created by the user. So the general idea is create that zip file, configure that zip file as a login item, which for some strange reason we're able to do within the application sandbox. Some of the guys over at SpectreOps have done some pretty cool work on this. If you want to understand the kind of details and the nitty-gritty of that, go away and have a read of their research. I believe it should be linked to in the labs post. So general understanding is we're going to place this zip file into the user's home directory. The login item will point to that zip file, and whenever you create a login item, when it opens, Apple will look for the default file handler for that type of file, which in this case is going to be archive utility. And thankfully for us, it is going to extract our ZSH environment file from that zip archive and drop it into the user's home. So whenever he starts up shell, this is going to trigger, and then hopefully we can get some sort of payload back. Cool. Now onto the video side of things. Now we have pre-recorded the videos. Apologies if they are a little bit fuzzy. It's some difficulties with streaming this stuff. But hopefully we can all kind of see at least the general understanding of what's happening here. So for those of you that aren't familiar, as Luke mentioned, go and have a look and play with APFELL. Here we're within an operation. We currently don't have any active callbacks. And the first thing we're going to do is create our APFELL payload. So this is just pretty simple. We're selecting macOS. We're then selecting just the standard HTTP payload with both APFELL and Poseidon. We're going to configure it to point back to the APFELL server we're currently running on. Nothing fancy, no redirectors or anything like that going on here. We're kind of keeping it nice and simple. We're going to select the APFELL payload from this, and the rest you can kind of customize however you like, provide whatever your name or kind of description you fancy. If you're interested in the kind of underlying workings of APFELL, there's plenty of documentation out there. They've done a really good job documenting how to use it, so feel free to go away and have a look at that. So now that we've created our payload with kind of all of the commands built in, we're going to download it and then we're going to start hosting it on our server. So on the same server we're running APFELL in this instance, we are going to just run up a Python web server on a different port. So I think we've gone with 8787 here. And at which point we're then hosting that payload for something to reach back to us. So now we're going to go into Microsoft Word and we're going to create a payload. The name you put in here doesn't actually matter because we're going to rename it to auto open. Now, like I mentioned, we are using Cedric Owen's macro generator tool here, where effectively you just provide where the payload is being hosted and it will generate the content that you need to put within your macro. So we've kind of talked through what that content is going to do. We've talked through the fact it's just going to curl a file down, add that file or add execution permissions to that file, and then we're going to run that file with OSH script. And apologies for the sirens in the background. I live beside a busy road. Okay, so we have generated it. We now just need to chuck everything into Word. I think there's some random character at the end of this here in the video, but just ignore that. Just take the contents. And as you can see here, we've got what, a five-line macro file. It's pretty simple. There's nothing too fancy going on. We are running MacScript or using MacScript. Effectively just calls a command shell or an OS shell. So I think it calls like bash or sh or something along those lines. So we're going to save our file. Again, name it whatever you like. The general idea here is we're going to send that payload to the target. A few moments later, back in our APFELL server, hopefully, if our SpongeBob meme disappears, we're going to see a callback come back in. So we're going to see a shell pop back within our C2 server, and we can see our APFELL payload if we list that directory. So we can see our payloads on the device. We are now getting callbacks, and we're now going to create a shell command. So we're going to attempt to touch a file to disk, and you're going to see we're going to get operation not permitted. Now, again, that goes back to the sandboxing that we discussed earlier, which isn't exactly ideal. So we're moving on. We're going to try and break out that sandbox. You can see we have the ZSH file or environment file here, which is just calling a no-hub command, and then it's going and grabbing our payload or executing our payload. Pretty simple stuff. And we're then creating a zip archive with that ZSH environment variable, and now we're going to upload that zip archive that we've just created to the home directory of the user that we've compromised. Cool. So now that we've put in our remote path, hopefully everyone can see this slightly better than I can because it's pretty small on my screen. Like I say, we've just chucked this into their kind of home directory of that user. Once we've submitted it, thankfully, we don't need to do the manual work here again. Cody Thomas and his team have created a persist login item for all users functionality within MYTHIC. It's nice and easy. It does the hard work for us. Again, it's worth going and having a read about what this is actually doing. But for the purpose of this workshop, we're just going to call the login item, whichever we fancy calling it. And then we're going to provide the path to the ZSH, or sorry, the ZSH zip file or zip archive that we've just created. Now again, what's going to happen here is when that ZSH or that login item is triggered, it's going to extract our ZSH environment file back to the user's home directory, and it will be triggered the next time a shell is created. Cool. So we can see that that's being created. Everything's gone through nice and easy. And one login later, as soon as that login item triggers, you'll see we get a nice little shell back, which is always a nice thing to see. Okay, so we now have a shell. What does that mean? Well, we discussed earlier how we were kind of limited by the sandbox, the sandbox. So we're going to try and rerun that same command, just touching a file to disk, and you can see this time it's a success. We're able to write that file to disk. We're able to access the desktop folder, different folders within the disk, and effectively we have just bypassed the whole kind of sandbox restriction that we ran into during the start of this. So sandbox is great. However, like many security controls, it's not a silver bullet. There's almost always a way to get around most of these security controls. Okay, cool. So I think now that we've covered off the kind of initial attack here, we are going to go ahead and look into some detections. So Luke, I'll pass over to yourself and you can tell us how we can find out this is happening.
Okay, awesome. Okay, so yeah, cheers, Cal. So we've seen, as Calum said, sandbox is great, but there is problems. People do find sandbox escapes. That one that we've just demonstrated was released end of last year and it still works now. So they think there is full scope for these things to be abused. So we're now going to turn to detection and see what we can do to detect. So we're going to introduce the endpoint security framework here. So the endpoint security framework is essentially Apple's bid to kick security vendors out of the kernel. So prior to well, a few operating system versions ago, you could kind of install kernel extensions, you could pull all of your telemetry from there and kind of have free reign. Apple weren't a fan of this and have kind of prevented developers from using these kernel extensions. But to kind of bridge the gap, they've created things like the endpoint security framework and the network extension framework, which vendors and developers can use to see information about the system that would otherwise require kernel code. So how does this work from if you're like a developer and you want to use this, or if you're a vendor and you're building an EDR solution? Well, you need to register with the endpoint security framework, and then you receive events. So you get callbacks every time something happens, and you get kind of the information back depending on what you ask for. So we can ask for loads of different things. There's 51 different types of events that you can get, and these are useful data that you could use to detect malicious activity. So things writing to files, processes executing, processes creating new files, renaming. There's just a sample here of the stuff that I thought would be quite interesting. The last one is to do with process injection on macOS, but really useful telemetry. So in our labs and yourselves, when you want to kind of go ahead and look at this stuff, how do you access this without being a developer and writing all the tools yourself? Well, there's a tool from FireEye called Crescendo. It's kind of the modern version of monitor.app, and it uses ESF to collect this telemetry. So it's nice and easy to use. It's got a GUI, so it's super friendly, and you can see all the events that are happening. In our labs, we've gone with the Objective-C tooling. This is command line tooling. A little bit easier to show and to kind of grab through to find out what we want. And it's also slightly more verbose. This is Patrick Wardle's website if people haven't seen it before. If you're interested in macOS offense or defense, this is kind of like a must read really. And there's also, if you are a developer and you do want to kind of dig into the nitty-gritty of it and write some of your own tooling, all that information's on there as well. So super good resource. Cool, okay, so I'm going to cover the kind of blue side of things. I'm going to show you how to use the tools and how to like kind of find the telemetry and start having a look for it. The labs encourage you to kind of explore this more on your own. We're just kind of doing a summary. Okay, cool. Okay, so as I said, we're using the Objective-C tooling. We're going to start Process Monitor, which collects events to do with executing processes, and we're going to launch our document. So everything should have happened now, all of the offensive stuff that we've just saw from Calum, and we can start taking a look through these logs to see what we can find. So first thing, we can see it worked. We're actually getting telemetry back. We can see a whole bunch of entries for Word, which is good. And then we can further query this down. First of all, we're going to look for fork events. So for people that are on Windows and aren't familiar with this, this is just a method of executing additional code. So it forks itself, it duplicates its own process, and then can take a different execution path. So we can see Microsoft Word forking itself to execute something else, which is already starting to be interesting to us. And we can kind of dig into this a little bit further, and we can start searching for things like OSA script, and we can start to see some of our malicious activity. So we can see our script being executed. We can see it being, if we dug further, we'd be able to see it being curled in. And yeah, so this is kind of just brief look at these tools. In the labs, we encourage you to kind of go through, map up parent-process relationships and kind of dig into this further, and kind of really have a play with the data and see what you can see. Cool. Okay, so moving on to our next topic, launch agents and daemons. So we're now moving into the world of persistence. We've got code execution. We're talking about LaunchD specifically, and LaunchD is kind of the service management framework for macOS. It's been on macOS a long time, and it kind of manages everything that requires to persistently execute code. You can kind of think of it like Windows services, and malware authors absolutely love this technique. It's been around for a long time, and malware authors have just been using it a lot. So it's a really good one for us to take a look at, and a really good one to make sure you've got covered off for your detection platform. So I've mentioned two things here. I've mentioned launch agents and launch daemons. They are different whilst being executed by the same kind of solution. So an agent runs on behalf of the logged in user, and it only runs when the user logs in. And the launch daemon is more for the system. It runs as root, or you can specify it to run under a specific user account if you want. And this runs on system boot. But there's kind of more levels to it than that. So you can break this down further. You can see a whole different folders on the operating system which kind of correlate to the different agents and daemons and who they execute for. So you can see the ones that are just executed for your user. You can see the ones that Apple have put in themselves. And if you list these directories, you just see a whole bunch of plist files. Another way to kind of query this and take a look at this is if you use launchctl list, and you'll get daemons, agents, and a whole bunch of other stuff, but only for the user that you're executing as. So I mentioned plist files. What are those? If you're from the Windows land, you probably won't have heard of these. So they're super common on macOS. They're essentially just a file format for storing serialized data. They can get quite complex. You can kind of put loads of different stuff in there, or your kind of arrays, dictionaries, and standard data types can go in there. You can nest plists within other plists. And it's kind of, yeah, Apple's solution for config files almost. They come in two variants. You can have Apple XML, which is just plain text XML, open it in any text editor. It's really easy to see, really easy to read. And then you have Apple binary, which is the complete opposite. It's all encoded. You can't just read it, and it requires specific tooling. Lucky for us, a lot of this tooling exists on the box already. So just kind of going through from least to most sophisticated, defaults is a tool that's been on macOS for a very long time. It's quite good for reading plist files. Writing to complex plist files gets a little bit more difficult. There's a tool called plutil, which is very simple to use, especially when you're reading. You give the -p flag, point it to your plist, and it kind of puts it out in a nice format for you, whether it's binary or not. And again, writing is possible. It's easier than defaults, but when you're trying to do really complex stuff, like working with arrays and dictionaries, this can get quite difficult. And then lastly is a tool called plist buddy. And this isn't in the path, so you need to specify the full path, but super powerful, very complex. It's kind of got its own little language that you can use to write to plist files and read them and do all kinds of stuff. So if you need to do really complex things, that's probably the one to use. But if you're just reading, we can just do something like plutil, and we can kind of view these plist files. This is just an example in my launch daemons folder. Something that gets executed as the system executes. It's a privileged helper for VMware. So what's this look like for us? So as a offensive operator, we can create our own. It is pretty much as simple as just writing this file and putting it in the right directory. We need to tell it what we want to execute. We can say whether we want to execute when the user logs in or not. And we can also give it an interval if we want to execute something periodically. We can do that as well. And yeah, just put this in the folder. It will not execute on the same reboot. So if you reboot the system, it will then get loaded into launchd, and then it will start executing. Otherwise, if you do want that immediate execution, you can use launchctl with the load subcommand, point it towards your plist, and then load it straight away. Okay, and again, we've got the lab here. The lab goes into way more detail than we're going to now. This is just a super quick demo of how you can do this in APFELL to feed into the next blue section. So we've got our APFELL payload running. As Calum kind of mentioned, there's a lot of commands in here already that Cody Thomas and the team have wrote. We can persist via a launch agent. We can point it to where we want to put our plist file, and then tell us what we want to execute, any arguments, anything like that, and then give it a label as well. Fill in these parameters. Give it a nice name. And then submit. And then that will then go ahead, create our plist for you, put it in the right directory, and it'll all be sorted out. Cool. So is that video? Yeah, okay. So we're now going to move on to the blue side. How do we detect this? What can we do as defensive practitioners to detect this ending? And I'll hand back over to Calum.
thank you. So the defensive side of this gets a little bit interesting. There's kind of two challenges that we run into, but there's two approaches we can take to identify this kind of attack. So for those of you that were paying very close attention, one of the greatest challenges we face with launch agents is that they are used everywhere on macOS. That's a very legitimate thing for software to use. So therefore, the creation of a launch agent itself isn't necessarily malicious. In the example we used there, we of course pointed our PLIST to a binary, our launch agent to a binary, which can make things a little bit easier, which is something we're going to have a look at here. So for those of you that haven't used it before, OSQuery is a pretty awesome tool. It's not developed for security purposes, but it can definitely be used kind of for that reason. Is a very kind of high, quick overview of OSQuery. Its intention as a piece of software is that you can deploy it across your estate, and it effectively allows you to query the devices on your estate as if they were a SQL database. So it pulls the current status of pretty much everything on your device. In this case, it has a table called launch D, where it contains all the information of your launch daemons, your launch agents, your launch daemons, any kind of arguments that they have, how frequently they run, that kind of stuff. So having all this in a kind of SQL query or a SQL queryable manner makes life a lot easier, especially if you're trying to understand kind of how things look across your state at scale. It's a very kind of efficient thing to use. So in terms of what we're going to look at here using OSQuery, one of the hardest things about detecting malicious attacks using launch agents is that, like I said, that a launch agent being created is not necessarily malicious. It's the contents of that launch agent or what that launch agent points to that's likely doing the malicious activity. Now, you can directly run scripts from within a launch agent, but for the sake of this lab, let's just say we're pointing at a malicious binary that does something on disk. Let's just assume it's giving a reverse shell somewhere. So what you'll see on the screen just now is a OSQuery statement that I think it was believed it was developed by Guillaume Ross. I'm probably butchering that name, so apologies. But the general understanding with this and what this is intended to do is it's intended to look for launch agents and link up any binaries that those launch agents point to with OSQuery's database that kind of tracks the signature of files that are on your disk. So in this case, what we're going to look at for this query is any launch agents that point to a file on disk that is not signed. So we'll kind of discuss code signing in a second, but any unsigned binaries that are going to be executed by launch agents that also start upon load. So anything that's kind of there for persistence, if you like. So again, Luke, if you wouldn't mind moving forward, thank you. The code signing side of macOS is a really powerful kind of security pillar within the macOS ecosystem. The general idea with code signing is Apple wants to have some sort of control over what code can run on your device. So in terms of dropping a binary, you can't really just drop a binary on a macOS device and execute it. At least a lot of the time, you're going to run into some restrictions there based on Apple's kind of security control called Gatekeeper. The general intention here is that for any kind of code to land on a macOS device, it should have to go through some sort of review process to make sure it's not malicious. Now, as I'm sure we've all seen in recent industry research, that's not always the case. There's been quite a lot of notarized macOS malware, but that's for another time. Now, the reason it's applicable here is what's interesting about launch agents, and perhaps this is one of the reasons they're so commonly used by malware, is that launch daemon, so launch D, which is effectively what keeps all these launch agents alive, it doesn't run into the issue with Gatekeeper, and that launch D by default has, or will just execute any kind of binary that you point it to, whether or not it's valid code signed or not. So it effectively bypasses Gatekeeper, which is a huge part of Apple's kind of security. So there's quite a big hole there, and something that we can definitely at least take advantage of identifying with that OSQuery that we've just looked at there. So we're going to take a quick video. We'll demonstrate the OSQuery we've just looked at. But first of all, just for the sake of touching on it, Luke mentioned earlier that the endpoint security framework can be used for process monitoring. And he also showed a bunch of commands that are the likes of file monitoring. So we're going to show how you can kind of monitor for file writes that are to effectively a wildcard directory we're looking at. So here we're going to run Objective-C's file monitor. It's very similar to process monitor that Luke showed earlier. The general idea being we're going to try and run this, set off our launch agent so that we can see this on the device, and then look at any kind of logs it leaves behind. Cool, so running sudo file monitor, you can prettify this and just get a nice JSON output. However, for the sake of this workshop, we're just going to output it to a file, kind of quickly skip forward, and there is a gap in between these two events. But now that we've pulled all the file monitors events for about a 30-second period around the launch agent being developed, we're then just going to cat out that file that we've had. We're going to grep for anything that's in /library/launch, and then we're going to prettify it with JQ. Now here you can see that a file has been created and put into the user's launch agent directory. I'd advise you to go and play with this in your own device, or go and have a look at the labs post we've developed. I think I ran this on my device, and there's some weird kind of, it creates an initial file and then renames that initial file to the NP list. I'm not sure if that's because I use Objective-C's block tool, which, as someone's quite rightly put in the comments, is a really good tool for blocking these malicious launch agents. But yeah, kind of moving forward, we're now looking into the OSQuery side of things. So first thing we're going to do within OSQuery is we're going to look and kind of try and identify any malicious any unsigned binaries that have been run by launch agents on our device. You'll see that we have a bunch of GPG stuff, but what's of interest is we can see our plist file that we've just dropped onto disk. So you can see the path to the plist, and then you can also see the plist, the binary that plist file is then going and executing. So again, the kind of two sides of this are the file monitor attempt of detecting this in terms of monitoring for file writes to the launch agents directories or launch daemon directories. Is really good for picking up the creation of new agents. The OSQuery command is perhaps a bit more accurate in identifying kind of any malicious behavior of kind of anything pointing to unsigned files. Cool. So moving on, we are going to now jump into the third and final lab, which is bypassing TCC. Now, for those of you that have ever played around with any Apple devices, whether it's an iPhone or macOS, you'll likely realize that, especially as of late, you pretty much get prompted for access to everything. So even if you've never played with a macOS before, the majority of us have played with an iPhone, and whenever you open a new application, you get asked to access the camera, the location, and pretty much Apple likes this whole idea of giving users the option to say yes or no to any kind of piece of software on their devices accessing certain components. So for this one, TCC, which is the macOS control we're going to be discussing, it's not just a Mojave feature, that's just a typo left in there. I think it came in Mojave and has kind of been going forward from that point to macOS. The general intention there is to maintain a database on disk that keeps track of whether an application is allowed to access a certain resource or a certain kind of part of the device. So in this instance, let's take WhatsApp. We've got WhatsApp wanting to access the camera. It's going to use the TCC daemon to effectively go away, create a TCC database, and say, does WhatsApp have the necessary permissions to access the camera? Now, in this instance, that request has never been made before. WhatsApp's never asked for the camera access before, and as such, we're going to get a pop-up. So we're going to get a pop-up saying WhatsApp would like to use your camera. Now, whatever the user responds to this, the TCC daemon will take that response and effectively mark it in the TCC database. So it will either give it a value of the user's permitted it or the user has denied it. Now, what's interesting about the user denying is the TCC database is quite smart, and that if a user has denied like WhatsApp access in the camera once, it won't keep on asking. It sees that it's already asked the question and then doesn't kind of go back on that every single time. So this is pretty useful for ourselves, but it's also going to pose quite a challenge from an offensive perspective. So if we think about the scenario we're in, we are running an APFELL payload through OSA script, and we want to screenshot on the device, for example. Now, the only problem with that is unless the user has previously permitted that instance, whether it's terminal or iTerm, to monitor the screen or to monitor activity in the screen, the user is either going to get prompted saying, would you like terminal to access your screen, or it's going to deny you straight away. Now, if you're in an offensive engagement, it's not ideal to be going and just putting a query for everything you want to access, whether it's the documents desktop or, like we say, calendar or anything. It's a little bit clumsy to just go around requesting access to all of these and kind of raising suspicions with lots of prompts. So we need to find a kind of smarter way of being able to interact with the TCC database. So as we mentioned, we really want to gain an understanding of what we're allowed to do. But unfortunately, the TCC database is within an area of the user's directories that you can access. So it is specific to each user. So there's no kind of permissions or anything. It's not root protected, at least the TCC database that we're discussing. So we should be able to access it theoretically. However, there's a nice little control in place that a process is only able to access the TCC database if that program or piece of software has full disk access. So it's a little bit difficult. The chances of terminal having full disk access or iTerm or whatever you've compromised is a bit of a challenge. So we need to take this a kind of step further and find something that does have that full disk access that we need. Okay, so we mentioned earlier there's almost always a way around everything in the world of security, and in this case, the kind of chink in the armor here is going to be SSH. So for those of you who played around with this, SSH, obviously the remote management tool, is for administrators to remotely administer devices, as the kind of name infers. The idea here, and as to why it has full disk access, if you're remotely accessing a device, you can't be clicking on prompts permitting kind of access to documents and the like. So kind of by the nature of what it's doing, SSH needs that kind of full disk access to be able to do what it needs to do, which leaves a kind of hole that we can kind of take advantage of. Now on the right, you'll see the screenshot of the kind of security and privacy full disk access. Now what you'll see here is any processes that have, or any pieces of software that have that full disk access. You'll see in this screenshot that SSHD has full disk access. However, if you're running Big Sur, for example, it shows the SSHD keygen or something along those lines. Now, we've kind of included a link down at the bottom there for a blog post that Howard Oakley wrote on this kind of attack. I know Mikey Jack has also done a fair bit of research into this stuff. So it's worth going and having a read as to why there's some discrepancies in here. But the general idea is we've found something on the device that has that full disk access that we can abuse. So how we're going to abuse it? Now this attack relies on kind of one of two factors being applicable. We either have the user's credentials, the user we've compromised, we either have their credentials, which for macOS just throw up a pop-up and screen and ask for them. It's a nice little trick that's lasted the test of time. Or the kind of, and with that kind of factor, we also then need SSH to be enabled, assuming the user is an administrator. The second example or factor that we would need here, or condition we would need here, is that the user you've compromised is an administrator and you can yourself enable SSH from the command line. So we're going to just keep it simple, go for the first. We have local credentials for our user and SSH is enabled. And we're going to show you a video of how this kind of looks in real time. So hopefully everyone can see this. Again, apologies, I don't think Teams is too great for these live streams. But the first things we're going to try and do is we're going to list the downloads folder, and you're going to see that operation is not permitted. So this isn't something we'd do in an engagement normally because it would trigger a prompt. But to bypass this, we're going to SSH into our local host with the account that we've compromised. Now you can see once we've SSH'd in, we can list the downloads folder and therefore we're kind of showing that we're able to access that part of the device. Now, to provide the tool that we want to access permission to then go and access the downloads folder, whatever we need outside of an SSH session, you can see here we are selecting all from the access database, which is the kind of applicable database within the TCC database. We're looking at iTerm2 as being the client, and where the service, aka what it's trying to do, is accessing the downloads folder. So we can see by the kind of values there, if you go and look at them in the SQLite browser, they effectively align to no, that user's not allowed. They're denied access. So what we're going to do is we're going to put an update statement, and we're going to update that database to have values that we need. So we're going to update it so that that user or that account, or sorry, that program that we've compromised has that TCC permissions to be able to access the downloads folder. So once we restart the application, again, outside of an SSH session, as you can see, we have just granted ourselves the permission to access that component. Now, we've used the downloads folder here as an example, but if you think about how dangerous this can be when it's things like screen recording or access to camera, or even if it is the user's documents, whatever it is you're trying to access, being able to abuse the fact that SSH has that full disk access and being able to update the TCC database directly, it definitely gives us kind of something to go on from that perspective. So I believe we're now going to jump into some detection stuff from that, the kind of blue side of things. Luke, if you want to take it away.
Yep. I just want to call out, there's been a really good question in the chat about can we just compromise a process that already has TCC privileges and then use theirs, perhaps using something like process injection. So yes, process injection on macOS is really is not the same as it is in Windows. You can't just arbitrarily inject into processes. There is research that allows you to do this in a few different ways. There's a blog by Adam Chester, XPN, called macOS Injection into Third-Party Frameworks, where he uses some quirks with the way that Electron apps work to inject code and steal theirs, and you can do it to Slack and a few other things. It's a really good read and a really cool technique. Yes. Okay, so moving on to the blue side. There's a few different ways of doing this, which we cover in the labs, but the new defensive control ring going to introduce here is the concept of a network extension. So this is the network portion of, I guess, the network counterpart to ESF. You can do all kinds of stuff with this, not just security things. So tools that want to play with a VPN and do VPN things will need to use the network extension framework. But the one we're interested in is on-device content filters, or like a proxy that runs on your own device. Like personal firewall is probably a better way of saying it. So, for example, again, Objective-C, we love Objective-C. One of their tools is called Lulu, which is a personal firewall. Uses this framework, and you can kind of see what your device is connecting to through this. We don't have a more detection-focused tool that utilizes this. At least not one that I could find. So we're going to, in the labs, show something called Netiquette, which is kind of similar, but instead of logging constantly, it's a real-time view using system utilities. Yeah, as I say. Okay, yeah, so we'll start the video. We're going to start our TCC attack, SSHing locally. We can see on the right there that SSH is connecting to the local device. Note that it's connecting over IPv6. And this is just really weird behavior in general, right? So an SSH process connecting to itself, connecting to the local host, is behavior that is probably alertable for something like this. We've exported the logs, and we can go through and we can see that on the left. And then we've kind of got another strategy here as well of actually detecting weird writes or reads to the TCC database. And this leverages the file monitor in ESF that we've shown previously. So we're going to collect the events, we're going to run the attack, and then we're going to show that something other than the TCC daemon was messing with this database. We can see in the logs here when it comes up that it was SQLite 3, which is super weird and super kind of obvious that something dodgy has gone on, because to my knowledge, only the TCC daemon ever needs to interact with this database. So that is another avenue to explore in the labs as well. Okay, cool. Okay, so that was our last lab. I'll move on to a few conclusions just to wrap up kind of the stuff we've done. So on the offensive side, we've taken a look at Office macros, launch agents and daemons, and bypassing in TCC to access the file system. And we've got labs for all of those. And then on the defensive side, we've looked at a whole bunch of controls that are present on macOS devices. We've got sandboxing, ESF, code signing, note extensions, and then also the one we brought ourselves with OSQUERY. We did want to take a second and just do massive shout outs to kind of all of the researchers in this space that have that a lot of this is based on. I'm not going to read them all out, but there's inevitably people we've also forgotten, but yeah, wouldn't be possible without them. Which ends this workshop really. So kind of plug for next week. Same time next week, we're going to be covering AWS, which is going to be really, really cool. So make sure you attend that as well. We'll stick around for 10-15 minutes, I guess, answer questions if there's anything that comes up in the chat. And otherwise, have a great rest of your day. And we'll hopefully see you next week.
Thank you all very much, everyone. Just as a quick one, for anyone that doesn't have any questions just now, you can always reach out to Luke and I on Twitter or anything like that. We're fairly responsive there.
Kind of feels like we need like elevator music or something now.
Why do you think we have Alpha here?